Hello, welcome back to wide delta three-phase circuits. This is problem number 4. This is a fantastic example of something that looks really challenging that actually isn't challenging if you have a good bedrock and draw some pictures and kind of understand what the problem is actually asking you to do. So here's the problem statement. This is what you would be given on an exam or a quiz. It says the line voltage at a delta connected load is 208 volts. Each phase of the load is a 5.2 ohm resistor in parallel with a 6.933 ohm inductor. That's the impedance of the inductance anyway. I guess we didn't give it in henries, we just gave it in terms of its impedance. What is the magnitude of the current in the line feeding the load? Now the first time you look at a problem like this, you're usually worried about it because you've never seen anything quite like this where it says that each phase of the load is actually a parallel combination of two things. So number one, you're probably thinking, how do I draw that? Number two, does that mean I have to do everything twice? Number three, well, there is no number three. That's just 1 and 2, right? So there's a lot of questions. But anyway, if you draw it, you'll get there. The other thing that's interesting about this problem, two things I want to point out before we solve it, is it gives you the line voltage and gives you 208 volts, but we don't give you the phase of that. I don't give you 30 degrees, 40 degrees, 0 degrees, or anything like that. And also, at the end of the day, it's not asking you for the phasor of the current in the line, it's asking you for the magnitude. So let me give you a little tip. When you see any problem that asks you at the end of it, give me the magnitude of something. Like, give me the magnitude of the line current, give me the magnitude of the phase voltage, give me the magnitude of something. Then generally that means that we haven't given you enough information to find the full phasor of whatever it is they're asking you for. So at some point along the way, you're probably going to have to make some guesses about what the phase information is, some educated guesses, or you'll have to be careful with the equations, knowing that you'll have to throw the phase information away at the end anyway, because ultimately they're only asking you for the magnitude. So here when we say, what's the magnitude of the current in the line? In other words, that's the line current, right? IAA, typically. But we're only asking for the magnitude. So that means typically we haven't given you enough information to find the full phasor of that guy, which makes sense because I didn't even give you the phase information of the line voltage to begin with. So let's kind of take that into consideration and go through it here one step at a time. Before we start getting into the calculations, we need to decipher this sentence. Each phase of the load is a resistor in parallel with an inductor. So what does this mean? It means that we have a delta connected load, we have a black box here and a black box here and a black box here. But in this particular case, we're given some information about what's actually inside the black box. So don't start doing things like, here's a delta load and I'm going to draw another delta load in parallel. We do have problems like that actually, but it'll be more clear. It'll say a delta load is placed in parallel with another delta load. Or it might say a delta load with this information is in parallel with another Y connected load. So you can have a delta in parallel with another delta or a delta parallel with another Y load, but that's not what we say here. Here we're saying each phase of the load is a parallel combination of something. So what that means is, I guess I'm going to have to use my finger here. For phase A, right, we know a little bit more about what's in here. So let's draw what we know. It says each phase of it is a resistor in parallel with an inductor. So the way I want you to write that is, let's go down here, is the following. This guy is a resistor, and it's in parallel with an inductance. Do you agree that that is exactly what the problem statement says? It says each phase is a resistor in parallel with an inductor. That means that whatever these values are, which we're actually given these values, the exact same thing is happening inside of this box where it's a parallel arrangement of two things, and the exact same thing is happening inside of this box, which is a parallel arrangement of those two things. So now that you see that, it becomes a lot more tractable because this is 5.2 ohms. I'll write it right here, 5.2 ohms. And the other one is a weird number, so let's just put it, I guess I'll do it down here, right? This is 6.933 ohms, and it's an inductance, so you know it's J, positive J, 6.933 ohms, okay? So what you have is you have a parallel connection of a resistor and an inductor where we're already given the impedances. So whatever we're driving the circuit at, I could give it to you in henries, but then you'd have to know the frequency of the circuit to calculate the impedance, but in this case we're just given the impedances. And that's what we have. Now let's look at what else the rest of the problem gives us before we formulate our strategy. It says the line voltage is given by 208. That's all we know. Now we know that this parallel combination exists here, it exists here, it exists here. So we have to figure some place to put the 208. So what we're going to do is we're going to put it over here. We'll say that VAB is equal to 208, right? That's really the magnitude. If I really wanted to draw it, I could put magnitude is equal to 208, but I'm going to kind of put a 0 degrees here, but you just got to realize that this 0 degrees that I'm putting here is really not given in the problem statement. I'm just going to kind of carry it through for now, and I'm probably going to throw it away later. The right way to do it, I guess, you could just say that all we really know is the magnitude of this line-to-line voltage is equal to 208, but it's something in this circuit has to be 0 degrees, typically, in order to be a reference. Something has to be the reference. Either it's going to be the line current, or it's going to be something at the generator side, or something. So since we don't know anything else anywhere else anyway, I'm just going to say this is the reference. Everything else is going to be measured relative to it. There's really nothing wrong with that, since you're not given any other information anyway. But just know that this phase angle may not be totally right, depending on what the rest of the circuit actually is. Okay, so now we can actually solve this problem, believe it or not. It says we want to find what is the magnitude of the current in the line feeding the load. That is IAA, this guy right here. So I can label that. I can label IAA. I'm going to do it way up high to not get in the way. I little a, big A. That's the current going in here. So we have everything here. We have a load impedance, it's a parallel combination. We know the voltage across is 208, and we know we're trying to find IAA, which is the magnitude of the current feeding this load. Okay, feeding this load. Now the first thing to remember is that because these are in parallel, we know how to find parallel combinations of things, so I can find out what Z delta actually is. It's a parallel combination of these two things. So if I wanted to do that, it would be the product of these two things, 5.2 times J 6.933. The product of their impedances over the sum, 5.2 plus J 6.933. Remember, when you have any two elements in parallel, you can just do the product over the sum. That's the shorter way than doing the full-blown calculation. This is very valid to do in the case of two things. And so what I can figure out is that Z delta is actually 3.33 plus J 2.50 ohms. Okay, so what we're basically saying here is that this parallel combination can be written as, even though in reality the box really is 5.2 ohms, and parallel with this, it can be written as a kind of in a series, in a linear fashion, as a 3.33 resistor with a different inductance if I were to write them in series. So I'm just basically converting that parallel arrangement into a series relationship. Why do I want to do this? Why do I want to find the parallel combination and figure out what this is? Because ultimately what I'm trying to figure out is I want to know what the magnitude of the current in the line feeding the load is. So I want to know, I know, well, let's go back for a second and figure out what the strategy actually is, and you'll see why. It's helpful to have it in terms of one impedance instead of a parallel of two, because I know this voltage here. That means I know the voltage across this impedance, right? So if I know the voltage across this impedance, then I can find the current through this impedance. But I can only do that if I actually represent the parallel combination and get it reduced down to something in series. Then I can find the current through here. Once I know the current through here, I can do a current shift to give me the line current. Because this is the phase current for the A phase, I can shift it back to being the line current for the A phase. So the strategy is, I know the voltage here, I know the impedance, I'm going to find the current in the phase, and then I'm going to do the square root of 3 shift to give me that guy. All right? So let's go ahead and do that right now. Let's go ahead and figure out what that is right now. IAB, which is the current going through that phase of the load, is going to be VAB, whatever the voltage across that is, divided by the impedance itself. I is equal to V over R, Ohm's law, right? But VAB, I know, is given in the problem statement. Now, really, I'm only given the magnitude, but because I'm dealing with phasors, I'm going to represent it as a complex number with a 0-degree phase. You can do that, as long as you remember that it might not really be 0, but certainly you can take it to be 0 in this problem statement. Then, divided by the impedance I just calculated, which is 3.33 plus J 2.50. Okay? So then the current through that phase is going to be a magnitude of 50 at an angle of negative 36.90 degrees amps. Now again, this phase angle might not be right because I took it kind of comes from this and it comes from the phase information of this. Because I kind of made this up, so to speak, at 0 degrees, I mean, if this really were negative 50 degrees, it would change the phase angle. But remember, in the end of the day, what we're trying to find is the magnitude for the answer. The answer we care about is the magnitude. So the most important thing is that we get the magnitude correct here. We need to carry some phase information through because this phase information carries the phase information of this impedance in with it. Okay, so the way that you do this is if you have magnitudes that you're actually asked for in your answer, you don't need the whole phasor. Carry the calculation in terms of a full phasor as far as you can, then just throw away the phase at the end. That's really the best way to do it. So that's what we're doing. We took 0, we divide. We're saying right now this is IAB. This is the current going through here. Okay, now there's a rule to go from shifting between phase current and line current. You all know what that is. So let's go and do that right over here. And what is that rule? It is IAA, the line current, is the square root of 3 times IAB, that's the phase current, and then it's going to be minus plus 30 degrees. Okay? So if we know the phase current AB, and we know all of this stuff, we just multiply and then we're going to get the line current. So boom, we're easy, we're done, right? But then you realize, wait a minute, I got to choose which sign this is. What phase sequence is it? Is it positive or negative phase sequence? I read the entire problem again and you realize there's no phase sequence information in the problem at all. I don't know if it's positive or negative phase sequence. So if you're not careful, you'll get stuck there and you'll be fiddling around with it trying to figure out what you're thinking is, why your thinking is wrong. Must be something wrong because I can't use this equation without knowing the phase sequence. But then you realize, actually it doesn't matter. Because when you think about it, I'm going to take, really what I'm going to do is I'm going to take this current I found, the phase current, I'm going to stick it in here. So this is a phasor, that's magnitude and phase. If it were a positive phase sequence, I would choose this, which means I subtract 30 degrees from the phase. But at the end of the day, I'm only asking for the magnitude of the line current, magnitude of this. So I would throw the phase away anyway if I subtracted it. If it were a negative phase sequence, I would choose the bottom sign, so I'd add 30 degrees to that phase. And then I would get a phasor. The magnitude will be the same in both cases. The phase of this answer would be different depending on what I chose here, but I'm throwing the phase away anyway, so it doesn't matter. That's how you get around that, and that's actually another one of the reasons why they only ask you for the magnitude in the end. So the way to really kind of do it, you could just choose positive phase sequence, and you could totally do that and then just throw the phase away, but another way to do it is say you're to the end of the problem. Because you know it doesn't matter, no matter how you go, you can say, well, the magnitude of this current is just going to be the square root of 3 times the magnitude of IAB. Because the phase information doesn't matter anyway. And so that means that it's going to be magnitude IAA. Well, let's just do it this way. Square root of 3, what is the magnitude of this current? It's 50. We already got that there. And then you multiply those guys and you get 86.60 amps. That's the answer. Again, I want to stress that when we calculated this, we have a phase angle. We're not sure it's right because we had to make some assumptions, but we could have taken this whole phasor and we could have stuck it in there. We could have chosen a positive phase sequence or a negative phase sequence, and that we would add or subtract the phase angles, and we would have a full-blown phasor for the answer, but then we would just throw the phase angle away anyway because we're only asked for the magnitude, right? So, real quickly, how do we do this problem? The only real catch to it is you have resistors and items in parallel for the load. So draw them in parallel. Do the combinations so you get them in terms of a single impedance, single, I guess, series impedance instead of parallel impedance. You know the voltage across, divided by that impedance, you know the current, and then you shift the current. And then you just have to do some thinking about what do I know, what do I not know, and when can I throw away that phase information. So we always do as much as we can with the phase all the way to the end. I'll tell you one thing you don't want to do. Some students will read this problem and they'll say, well, I'm only asked for the magnitude anyway at the end. So what I'll do is I'll calculate this impedance here. And see, this is an impedance, right? It's a complex number. I can convert this to magnitude phase. Of course you can. You can convert any polar number to, or any rectangular number to magnitude phase polar, right? Then when I calculate the current here, I'll just take 208 and I'll divide, instead of by this complex number, I'll just divide by the magnitude of this. So I'll take this and divide by the magnitude. I don't care, I just care about the magnitude anyway at the end. Then that'll give me the magnitude of this, And then I'll come over here and then I'll multiply and I'm going to get the complete wrong answer is what you're going to get. Because the reason is you have phase information locked into this thing, which is going to affect things down the road. I'm not going to sit here and say that some problems you can't get away with that, because sometimes it's simpler and sometimes you can. But in most cases, especially for more complicated problems, if you start doing this kind of thing too early and throwing away phase information too early, then you're not going to get the right answer. And so instead of trying to figure out which cases you can and which cases you can't throw away phase information so early, my rule of thumb is do everything in phasor notation. Even if you have to assume a 0-degree phase, do everything I can here. And then you could take this phasor, stick it in here, add or subtract, throw it away. It's just that when I got to this point, I realized no matter if I added or subtracted 30, the magnitude of the answer would be the same anyway. And so I was convinced that I didn't need any phase information anymore, so that's why I was able to do this. But in general, don't start throwing phase information early in your problem away just because you're asked for magnitudes in the answer. That's a good way to get into trouble. Eventually, if you start doing that, you'll get some problems wrong because there's a lot of phase information locked up in these impedances, which affect how the calculations proceed. And that's something I can't show you without a concrete example. You have to trust me. I've gotten into trouble doing that myself before. So make sure you understand that. Finally, we're done with the baby problems. We've understand how to shift. We understand more or less what the types of problems, how they're organized. Next lesson, we'll have our first full-blown problem, where we'll have, source, line, and load. But now that you know how to handle the load, we already know how to handle the source and the line, we already know how to handle single-phase equivalent circuits, so putting all the pieces together is going to be very easy to do. You'll see that in the next problem. So make sure you can do this one yourself and then follow me on to the next lesson. We'll tackle it right now.